All right. So sorry about that. Whoever is watching online, I forgot to press record. So what we're talking about is that if you have a person in a spaceship during acceleration g, light would bend in this direction instead of going straight to the system. And basically the acceleration is making it so that the light curves. If the person was not accelerating, but was traveling, the light would be going straight, but it wouldn't hit exactly the same point. And then due to the equivalence principle, if you're just sitting somewhere on Earth on a gravitational field, the acceleration is not there, the velocity is not there, but what you would have is that there's a gravitational field and the light would also bend in that direction. All right, with that, once we established that, Einstein said, okay, this is the same thing that happens in space-time. Mass is gonna bend the fabric of a space-time, and now light, instead of looking like it's going straight to space-time, is actually taking this curved path like this. And therefore you would see gravitational lensing. So let me show you an example of gravitational lensing right here. So do you guys know what this is? This picture right here? Anybody have an idea of this? What is shown right now on the slide? No? So this is something that Einstein predicted in 1912. He said, due to the mass of a heavy object, let me give you now the schematic. Due to the mass of a heavy object that is in between us and a star, so let's say this was a heavy object, is bending the light, and instead of, we have a galaxy over here, and the light of the galaxy is coming straight at us, but it's also coming in this, let's see, in these other directions, and these other directions, because of this very massive object bending the space-time fabric, the light actually bends back down in this direction and it reaches us. So we would see that this object looks like it's actually different objects, and this bending of the light due to the massive object passing the light nearby and bending the light over gives us something that now looks like the Kool-Aid man over here. So this is not two stars or the eyes of the Kool-Aid man. It's actually one single galaxy that is that the light, as it travels towards us, that it was traveling in this direction, the heavy object bent it this way, and now the light is going in that direction back to us, and we see it as two images. So this is one of the effects of special relativity predicted by Einstein in 1912. Questions? So this is called gravitational lensing, and that's an important effect because it was predicted by Einstein in 1912, the gravitational lensing effect. And he made the calculations to see how much light would bend. And then, because of this lensing, he actually said that you could go during an eclipse. So we know where the stars are located anywhere. So if we take a picture of where the stars are, we actually know, we point our telescope, we point it in some direction, we know that a star is located, let's say at this point. But then he predicted, because of gravitational lensing, the bending of the light, if we had a solar eclipse, the solar eclipse makes it so that the light, a total eclipse will make it so that the light gets reduced from the sun reaching us. And when we're in this point, the light of the sun is not reaching us. We can now see the stars again. And then seeing that the sun is there as the light is coming from a star, it wouldn't look as if the star is located here. It is still located here, but the sun is bending that light coming from us. And so the star would be located and shifted from where it should be. And so he made this prediction, and he said people should go and look at this. And he said, this is predicted in 1911. He calculates how much light is going to be bent with. And then there's an expedition to go see the solar eclipse somewhere. And they looked at, actually the first expedition didn't work because it was too cloudy. But then there's an expedition in 1910 where people looked during a solar eclipse and they saw that the stars near the sun were observed to be shifted a little bit from where they were supposed to be. And that was exactly what Einstein had predicted from his general relativity. And it's actually what makes him world famous at this point based on this different bending of the light. Questions? So then later people came up with, well, if the sun can do this, what would happen if we have an actual galaxy, not just the sun, but actually galaxies in between the light coming to us from ancient galaxies? And that's actually this picture that we see here. So this picture that I'm showing now is different galaxies, and the light is bended and it looks like this particular object. So that deflection was predicted, excellent agreement to what was measured, and is what makes Einstein really famous. Questions? No? All right. So then everything makes sense, I guess, right? That's why there's no questions. So at this point, I want to tell you about something else, not just lensing, but then moving to a different topic. And this is the field that is called cosmology. But it's also related to physics, and it is a subset of physics. It uses general relativity and other areas of physics to figure out what is going to happen to a star in the future. So how many of you know what is going to happen to the sun in, let's say, 5 billion years from now? Anybody know that wants to contribute about what's going to happen? I don't know if you guys have read about this, maybe before, or seen it in movies or something like that. Supernova? So you're thinking the sun is going to go supernova. Everybody knows what a supernova is? So actually the prediction, so this is what this field of astrophysics, or also called cosmology, studies. So it looks at a star and then it tries to figure out what's going to happen to the stars, right? So what's happening, how does a star get formed? That's the first question I want to cover. If you look at the early formation of stars, is that you have a lot of mass, maybe clouds of gas, usually hydrogen and other things could be in it. The space is full of it's not dense, so it's not like even like our atmosphere, but it has gas in between. So what happens is that there might be an object and it starts attracting the gas around it. And then that gas gets attracted and more gas gets attracted and more gas gets attracted. So if you look at a planet like Jupiter, Jupiter and Saturn, those guys are giant gas planets. They might have a core inside of them, maybe made out of um, maybe made out of rock, but the reality is that they're covering gas completely. So if you're just the size of Jupiter, which is quite huge, you just get stuck as a gas giant, gas planet giant. But if there's more mass around you, you get more mass, you get surrounded by more mass, and you're gonna have that as soon as you reach a really big size, bigger than Jupiter, but smaller than the sun, you can have that a reaction starts to occur because of the all of that mass, the gravitation of it is making it so that you start seeing that the hydrogens get pulled together so hard that they start collapsing into each other and forming helium. So that's what's happening to the sun, right? It's a giant gas of hydrogen, mostly hydrogen, with helium, with lithium, with other elements inside of it, but mostly hydrogen. And the reaction that is happening there is that the gravity is so strong that it pushes the two hydrogens together, and then you have helium coming out. And that energy is fusion of the nuclei. That energy is what we see as the sunlight and what makes the temperature of the sun so high and all of that. So if you're a star like the sun, what's going to happen is that you're going to sometimes run out of hydrogen. And you're this massive thing that is just going to be a huge, I mean, the hydrogen runs out, and now you have that. So the pushing together of the hydrogens and turning them into helium, the fusion reaction, makes it so that there's a lot of pressure in it that keeps it big enough at the size that it is right now. If you have only helium, you have more helium than hydrogen, and it's hard to continue doing that reaction. What's going to happen is that the sun is going to get bigger and bigger and bigger. And it's actually predicted that because of the mass of the sun, it's going to go and become maybe the size of it is going to be so big that it's going to engulf Earth. So our planet is not going to survive that. So that's not going to happen for 5 billion years. So we're halfway through the life of the sun right now. Afterwards, that huge expansion is going to be that there's no more energy to expand because the helium is being used up too, and it's going to come back into itself and turn into a little collapse into itself and turn into a brown dwarf. That's what it's called. So, or a white dwarf, sorry, for the sun. So that's when the gravitational collapse is going to happen, and it's going to turn, our sun is going to turn into a white dwarf, and you're going to have that it's going to be a red giant for a while. So now if you see another massive star a little bit bigger than the sun, like I think it's 3 times the mass of the sun, then that's that type of the size of it makes it so that it can go supernova and it becomes super bright for a while, and then it collapses into itself. But the sun is not going to go supernova. It's not massive enough. So now what people have seen by observations is how big things have to be. So for instance, you can be a white dwarf, like our sun is going to be. If you have a more massive star, what happens is that when it collapses, there's so much gravity around it that it basically strips, it forces the electrons and the protons to combine. The electron and proton combine and form neutrons and expels neutrinos. And then the neutrinos take away a lot of energy out of the sun. So this is what happens and it turns into a supernova. So you have that the star is so massive that when it pulls back itself, it pushes the electrons into the protons, it makes them into neutrons. Doing the proton crashing into the electron makes it so that you have neutrinos pop out, and the neutrinos have a lot of energy, and you're left behind with, so that's the supernova, the light that we see. That I guess we haven't seen any because we haven't lived for long enough, but people have seen it during the last 1,000 years. And then you're left with a cold neutron star. So these stars, neutron stars, are basically not doing anything. They're super dense. And these super dense stars, I don't know if you guys have seen Avengers Endgame. I think that Thor is supposed to be grabbing neutron stars or something like that when they're making his new weapon. But the idea is that when they become white dwarfs or neutron stars or all of that, they're just super dense, very high density, and in a very tiny amount of space. So the sun is going to get super huge, the size almost to the Earth orbit or probably engulf the Earth. Then it's going to collapse into itself, and then it's going to turn into a white dwarf. If it turns into a neutron star, it would be more massive than the sun, but it's maybe just the size of 10 kilometers. Its radius is not even large enough. That's what a neutron star would be. So now, what has been observed too is that if you get higher than 3 masses of the sun, when that collapse happens, you get a black hole. And that means that it's not just, so the neutron star might be 10 kilometers across, right? So this is 10 kilometers. That's about the size of it. And its density is about 10 to the 13, the density of lead. So lead is the heaviest element that we know, right? So this is a neutron star. So initially it was a sun-like star, but 3 times more massive than our sun, and it turns into that. So what general relativity says is that what happens to a body, so here, this radius and this density is such that we can still see it, so it's not a black hole, right? But the question that general relativity showed, looking at the math behind it, they said, what happens if you have a body of higher mass and then the radius of it collapses into something, right? So we had talked before in our previous class, and in this one too, we saw that light is going to bend. And for instance, we were talking about there's a planet here, there's a force of gravity pulling down on everything, right? It would make even light moving in that direction shift its frequency. So the frequency of this light is going down because of the gravity around it. And we talk about what happens if the mass or the force of gravity on it is high enough so that it basically freezes and it doesn't let the light vibrate anymore. And I believe Arthur said it, right, that it was going to turn into a black hole. So it turns out that general relativity allows for when a body has a big enough mass, so let the mass grow all the way and then let the radius get smaller. And then it turns out that if the radius gets to be, this is the gravitational constant, m over c squared. So this is a constant, constant, constant. The only thing that we're changing is what is the mass of the system that we're looking at. So if you have a high enough mass, if it collapses into a radius that is about this size, then you have reached the, this is called the Schwarzschild radius. And let me spell it. So Schwarzschild is the person that did this calculation for the first time. And he realized with this calculation that you would have something that light couldn't escape. The gravitation is going to be so big that it couldn't escape. And that becomes a black hole. So one of the most interesting things is that general relativity predicts this radius. And there's a crude way to do it because people did it actually with Newtonian gravity, thinking about it this way, but general relativity has about the same radius, but it's the correct one. And with this, we would have a black hole, which basically has an event horizon around it where light cannot escape. So in this case, anything that is outside can go in, but once it's inside this event horizon, it can never go outside of it. So you can treat it as a singularity, like everything inside of it. We don't know what really happens, but basically the idea is that this is a black hole, and it's a singularity because it's a point that it's kind of like a point that everything would collapse into it. And that would happen according to our measurements. It does happen, and we have seen them. And people have discovered ways to look at them. So I don't know if you have questions about black holes. For the next class, I wanted to cover what happens when two black holes crash into each other. But if you have questions about black holes, I guess this is the best we can do right now. Describing what's happening inside of them is impossible, but just how they form and how big they have to be is something that we have access to. Questions? All right. So if you don't have questions, that's it for today. And I'll see you all next week.